Hi everyone, thank you for connecting to our talk. Today I'm gonna talking about binary purging with Snapshot assisted driven comparison branches analysis. I'm very excited to speak at here and happy to share our research with you. Many binary purging tools use mutation testing, then randomly generate test cases. Despite a lot of progress in mutation-based purger, there is an issue of taking unnecessary time to evaluate conditional branches that compare complex inputs. If a program requires a lot of input, it's much more expensive to generate it. So purging result may vary significantly depending on how well you perform the input generation. For these reasons, modern purger adopt input generation to support mutator. In this talk, we introduce our approach of input generation. Before I actually start, quick introduction about myself. My name is Ki-jong Son. Currently, I'm security researcher at KISA. KISA Internet Security Agency in South Korea. And also, I'm teaching penetration testing courses. And previously, I was bug bounty program manager. At that time, my duties was to judge how critical vulnerability is and report root cause analysis of vulnerability to the vendor. I'm focusing mostly on vulnerability and exploitation research. So this is a summary of our talk. First, we are going to talk about why purger lead valid input generation before software purging, and why we implement this tool. And then for better understanding, we introduce the whole design of our tool called the live branch. After that, we are going to give on detail about how each of the stages is implemented and what we can do better to improve purging result. Next, I will describe how we can automatically extract input comparison value from binary. Also, I will explain how to connect between purger and live branch, which is our branches analysis tool. By the end of the talk, I will show you simple demonstration. So motivations. A traditional problem in purging is purger tends to get stuck in input validation code during deterministic purging stage. So purger wastes so many energies to satisfy input validation check. In order to solve this constraint, we need to supply feedback to purger, such as valid input. You know, most software vulnerabilities are highly associated with user input. So test case generation is becoming more and more important part of purging. Basically, test case generation can be divided into two types, mutation and generation. The mutation is to find the vulnerability with randomly generated inputs. However, it takes a lot of program execution attempt and time to explore a deeper path. For example, programs that has multiple inputs, such as command line or interactive application, has more comparison branches that hinder deep purging. So some mutation-based purger support user-supplied dictionary. This dictionary consists of input keywords for feedback. However, manually making an input keywords is very time-consuming. It requires human effort. I don't want to spend too much time for this. So we needed the functionality which can automatically generate interesting input for purging. Here is a simple example of why input generation makes better result. As you can see, we have 3 screenshots. The screenshot below shows simple C program for testing. This program first compares user input with a 6-byte string. And then if it's equal, we are able to move on to the next pass, which exists buffer overflow vulnerabilities. And the upper screenshots is about 2 different mutation purging. In the left upper window, it mutates without any input knowledge, so it wasn't able to find your path within the given time. On the other hand, in the right upper window, it mutates with input dictionary. We found you crash in 16 seconds. It shows that there is large performance difference. Also, according to our test, it took about 10 minutes to solve the 2-byte comparison string without dictionary. It turns out that a comparison of short-length characters can be correctly matched in a short time, even with mutated input. However, in the case of complex and longer strings, it needs much more inputs to solve branch. This is why purgers should adopt input generation. As I already mentioned in the previous slide, to reduce purging time cost, we need to generate valid inputs of the target program in advance. So possible question is, what's interesting inputs for purger? We can define like this: it's predefined inputs that are required by program. Some things that you may have noticed are things like option, command, file format, protocol specification, and so on. We have been investigating input comparison pattern in various binaries. It turns out that they tend to be compared at the front of the program after process initialization. This was an important point about the priority of tracing paths when you analyze the comparison branches. Basically, if a purger has input knowledge, it tries to achieve better code coverage, and then move on to the mutation stage to generate crash. What that means is that input generation plays a big role in detecting your path during purge testing. Input generation have been adopted by many mutation-based purgers so far, and it's very hard research in the field of purging today. Here are some input generation techniques commonly used by purgers. First, we can make a dictionary file which is referred to list of valid input, then use deterministic state. For example, American Purge Law AFL has several common dictionaries in the subdirectory. This dictionary can be provided by user or automatically collected by generation tool. And some purgers leverage the symbolic or concrete execution to generate the input. However, there is some well-known issue to be addressed. Symbolically executing program paths does not scale to large or complex programs, such as neural software. And purger can collect the seed template to generate the input on the internet. From this, it can provide multiple types of valid file formats. And we can also generate the input using binary or source code analysis. If we have source code access, it can be easier. But our research target is only binary without source code. Among these methods we introduce, what it decided to do is automatically make a dictionary using dynamic binary analysis. So how we run the input inside binary? For that, our approach is input learning with snapshot-assisted comparison branches analysis. Before starting this research, we reviewed the published research. According to our investigation, it seems that the input learning model for directly analyzing comparison branches has not been researched relatively. So we made a decision to use this approach. And also, we thought this might be interesting and challenging task. So before we introduce whole design of live branch, you might wonder why the tool name is live branch. I was inspired by the lighthouse. As a lighthouse is used to guide thieves, live branch illuminates dark area that other cannot see, and then it can guide it. That's why we named it. As you can see, live branch consists of three major components. Its dynamic control flow constructor and the taint analysis module and the branch analysis module. First, it actually loads and executes the target binary. Next, it tracks the flow related to input together with the support of Snapshot operation. And then we identify comparison branches in the execution path. Based on taint information, branches analysis module gather valid inputs by analyzing the operand value of the instruction. Main function of dynamic control flow graph constructor is to take a snapshot. It's actually snapshot engine. And it also controls taint and branch analysis module. For better result, these three modules work together organically. Now, why we need a snapshot for input generation? Snapshot is a technique that preserves data at a specific time. And snapshot is widely used in cybersecurity industry. As you can see our presentation topic, the core idea of live branching is to leverage snapshot as well. Here are reasons why we use snapshot. First, we use snapshot to skip over process startup code. Process startup code is unnecessary to generate input, because what we need to focus on is the instructions that executed after input functions. And we leverage snapshot to execute both directions of conditional branch. Basically, conditional branch jump to address depending on whether condition is true or not. However, we can execute both directions if we create a snapshot for conditional branch during process running. From this, we can increase the tainted branch coverage. As already mentioned, we use dynamic taint analysis. It has a disadvantage of tracking input only on executed paths. So comparing to static analysis, it has lower branch coverage. This is limitation in generating as many inputs as possible. But if we leverage snapshot, it can continue tracking tainted data by jumping other paths. So with this knowledge, we can achieve more comparison branch coverage. For these reasons, we can snapshot operation. Okay, now let's go over snapshot mechanism for input generation. As I said, like French use dynamic control flow graph constructor to create a snapshot. It generates control flow graph nodes representing code paths actually executed. But we don't generate every executed block. Only conditional branches are treated as graph nodes. Basically, control flow graph represents all the executed page blocks. However, our interesting point for input generation is page block where a conditional branch exists. So our control flow graph only consists of a conditional branch. And each node represents a snapshot. So it has a snapshot information. We restore snapshot by referencing these CFG nodes. We'll explain the type of snapshot information in the next slide. And the CFG constructor also made snapshot scheduling, like a snapshot creation frequency and timing. We implemented CFG constructor in instrumentation framework. To reduce overhead of binary instrumentation, like branch executes CFG constructor after detecting user input. So this is node container made by CFG constructor. Actually, each node container has a snapshot repository. It saves the execution context and memory state of a conditional branch. And it saves taint information as well. For preserving memory state, we record previous values of memory that have been modified during runtime. Memory snapshot will be covered in detail later. And taint information is used when executing a different path after snapshot is restored. This means that we can continue tracking taint propagation for other paths. These node containers are connected to each other using single linked list. Okay, now let's look at snapshot creation flow. First, we instrument header instruction of conditional branch with a callback function. And then, if callback is called, it saves runtime state of conditional branch in the node container. Node container can be divided into two types. If conditional branch is switch case, it's switch branch node. And other case is normal branch node. Why we divide into two types? Because these assembly code patterns are different. So we need to analyze nodes with two ways. Finally, if all the snapshots of the executed path is completed, it starts restoring snapshot under predefined conditions. We do this again and again until all snapshots have been restored. So when we restore snapshots, here are some conditions for that. If these conditions take place in target binary, we immediately restore snapshot. The key idea for restore snapshot is to detect leaf node. Leaf node is a node that doesn't have a child node in a binary tree. With this idea, we implemented the leaf node detection algorithm to identify restore point. If a program is no longer executing for some reason, we regard this last node as a leaf node. So we restore snapshot if it's at the end of main, or it's at the call to exit function, or we catch some process exception. Also, we need to check invalid instructions because we pause control flow to different nodes. We continued taking a snapshot until we met this kind of stop point. And the restore location is the head address of conditional branches page block. The reason we restore snapshot at the head is that branch analysis module utilizes page block level tracing. As you can see this slide, the page block which has exit core is the leaf node. So if a program executes leaf node, it tries to restore snapshot. And then snapshot is completed, we jump head of conditional branch to get ready to enter opposite path. Next, snapshot rules. For improving input generation, we applied some snapshot rules to right branch. First, there are two default rules. It doesn't take a snapshot for first page block right after restoring, because we have already extracted it on comparison branch. And another one is the restore node is deleted from the node list. Second, we have two optional rules. First one, we are able to set depth of the deepest node level. To implement this functionality, we assign unique ID to each node whenever creating snapshot. And this unique ID is determined by referring to the previous node ID. And depth of node is number of nodes on the path from root to leaf. If we enable this option, snapshots are saved only up to the depth level entered by user. This means that it leads to snapshot if node level reaches maximum depth. As said at the beginning of the presentation, program tends to compare input at the front end of program. So in this case, we can adjust the deepest node level so that can quickly analyze the front end of the program. This means that right branch can select the analysis range of comparison branch as this option. Another option is to configure redundant snapshot mode. Redundant snapshot mode is to allow to save the snapshot of already executed branch. For that, right branch could check and save whether the same conditional branch has been executed. Basically, there is no need to analyze its comparison branch again after extracting input. So we thought that we don't need to save a snapshot of the same branch. However, after several tests, we figured out a case where the redundant snapshot was needed. One of these cases is that we compare different values in same conditional branch, such as loop iteration. In this case, if we disable redundant snapshot, we couldn't extract input as many as possible. So for this scan, we need to set this option. Redundant snapshot operation affects the performance of input generation. Of course, right branch support memory snapshot. This is one of necessary functions to restore the execution state of a binary. For this, we first instrument all the memory writing instructions on trace level, and then it preserves original value of memory in their node container whenever hitting memory writing instructions. Memory snapshot starts from each conditional branch to write before being restored, and then we overwrite these preserved values back to the regions when restoring snapshot. If a value written to the same address multiple times, we record only first original value in same node. Next, how we traverse snapshot tree for this tour. As you can see, there are two strategies of tree traversal for restoring. These control flow graphs represent possible transition of conditional branch inside binary, and each node represents tree-based structure connected by edges. Case 1, bottom-up restore strategy, and case 2 is top-down restore strategy. So what's the bottom-up restore? Bottom-up restore is that it traverses tree backwards to the top node. You can see red circle and green circle in these binary trees. Red circle represents the conditional branches executed in the first run, and green circle represents the conditional branch that executes as soon as we restore. Like this, in bottom restore case, the restore location is circle 4, and then second run starts at circle 5. On the other hand, top-down restore is that it moves down on level from the top. This is also known as level order binary tree traversal. In top-down case, the restore location is circle 1, and then second run starts as circle 5. We tested both cases against real-world binary when implementing live branch. As a result, high performance is top-down restore strategy, because there are more comparison branch at the beginning of program. So it's more effective solution than others. Our earlier tool used bottom restore, but for these reasons, we had to change our strategy. Now, control flow hijacking. It's actually pretty simple. After restore snapshot, the first thing we do, we post jump direction to another path. In order to hijack control flow, we check flag status of conditional jump instruction, and then it moves in the opposite direction by referring to the jump bit. For example, if jump bit is true, we set instruction point to the next address of jump instruction. On the other hand, if jump bit is false, we move on to jump target address. Since we post execution of other paths, sensitive paths could be generate memory access errors. So in order to avoid this kind of behaviors, we check validation of instructions. First, validation of read-write memory access. To check invalid memory access, we collect currently mapped memory region and access permissions from mass file. We update this information before every check because of dynamic memory allocation and validation of indirect call address. Basically, indirect call takes the address from memory or register. So we check if it's in our code sections. And validation of null point access. It just checks if memory address is null. And last, validation of invalid free. For this, we create callback for heap memory allocation and free function using DBI. If a callback is called, we insert the allocation and free address in the list. So we can check whether argument of free function exists in the list. Also check double free with free count. When we detect this kind of memory access errors, we restore snapshot to find a different path. Now, snapshot for loop body. Basically, most of software have loop iteration code. And it's an open case that input values are compared inside the loop statement. So we investigated some real-world binary and tried to figure out specific disassembly pattern of loop body when comparing input. From this study, we found that it's used to compare byte by byte or multiple values. Live branch detect loop by monitoring jump address. If jump address is backward jump, it's loop. And also check if jump address is greater than function start address. Once we have extracted all the input values in the loop body, we don't need to analyze the loop anymore. So in order to avoid unnecessary analysis inside the loop, knife branch provides specific option. It's loop iteration threshold. For this, it counts the number of execution times of backward jump. If max loop iteration reset is reached, we no longer save the snapshot and restore it to escape loop. So what is comparison branch? Comparison branch compare with two operands and then jump somewhere. Examples of comparison branches are if-else and switch case statements. To better understand the structure of comparison branch, we analyzed the disassembly code of conditional branches in real-world binaries. From this, we figured out several patterns. First, as I said, input validation takes place more in the early stage of learning the program. This phenomenon is more pronounced when the input value is used as a command line parameter. Because command line parameter determines the program execution path. This helps us choose which nodes of the CFG we're interested in first when analyzing comparison branches. Second, there are some common use cases. The single branch compares one or several predefined values using one if-else statement. And the nested branch statement often appears when it needs to compare multiple inputs, such as an interactive application. It's also used when there are multiple comparison targets for single input. And loop iteration is often used when comparing string with byte to byte. In our point of view, we can divide the comparison branches into two types. Type 1 is input dependency branch, and type 2 is non-input comparison branch. What we are interested in is the input dependency branch, because it has a comparison value which we need to extract. So we discard non-input comparison branch. For identifying input dependency branch, we use dynamic taint analysis. Our initial seed inputs is random string for taint. There can be one input or multiple inputs in the program. Since the live branch doesn't know how many inputs target actually needs, we could execute the target with several random inputs. This is because unused inputs are automatically discarded. And our DTA module supports function level taint as well as byte level taint. Some library functions, such as data copy function, for example when copy, contributes to the taint propagation. So we implemented this function. And to improve code coverage, we can also take a taint analysis using the input values extracted through the control statement analysis. After identifying input dependency branch, we mark the tainted node in snapshot tree like this. This is helpful for branch analysis module. Okay, finally, comparison value extraction. Actually, we generate input at this stage. This is pretty simple than snapshot mechanism. Our branch analysis module instrument compare instructions and functions. You can see there are three types of comparison code we need to analyze. And these are commonly used inside the binary. At the CPU instruction set, we instrument to compare instructions such as CMP and test. Since the CMP command varies depending on the size of comparison, we investigated all CMP commands from Intel architecture manual. And sometimes the compiler optimizes code flow to REP assembly family. If REP assembly instruction is combined with CMP or scan string, it repeats comparison the number of times specified in counter register. So we also instrument repeat prefix instruction set. And it can compare input with function. So at the function level, we instrument standard compare library functions. In this case, CMP instruction is used to compare the return of this function. So we have to check function's argument, not CMP operand, when querying tainted information. If instrumentation callback with register is called, it tries to extract values through this flow. First, we need to identify location which actually has comparison value. Basically, comparison branch use CMP or test assembly instruction to compare input. However, as I already mentioned two cases at the previous slide, it might be somewhere other than CMP instruction. One of these cases is that it uses repeat prefix instruction set for input validation. Another case is that input validation is performed at the function level. So in this case, we need to extract comparison value in other location, not the operand of CMP. Next, we check which operands are tainted. With this knowledge, we can identify non-tainted operand, which has comparison value. And also, we need to check operand type. Types are basically register, memory, and immediate value. After identifying the type, extract value of non-tainted operand according to type. In CMP case, just get register memory or immediate value. And in REP prefix instruction case, get string from memory as the size of the counter register. And in compare function case, just get argument value. Knife branch mostly designed for extracting no value of target operand. Other values such as encryption or encoded data are not in scope for knife branch because it compares with transformed input, so we don't know its original value without code analysis. We tried to restore the original value by analyzing the type of transformed input. It turns out that it is very difficult to automatically analyze encoded or encrypted data without the original value. So it was very serious challenge for knife branch. Even if we analyze it, there is a lot of performance overhead. And also, after analyzing several binaries, we found that OpenSSL handles user input without comparison. As you can see in the right screenshot, this source code is user input processing function of OpenSSL. The command used in OpenSSL is converted to hash value and saved when initializing. And it gets point of digest module object only by user input. And then with this knowledge, jump function pointer of digest object. So there is no comparison value we extract. Also, this means that we don't know input value to jump fast. To do this, we need brute force input creation. But this is not in scope for knife branch. Okay, now comparison of values from offset. Binary often use indexing addressing to compare input. In this case, since the value inputted by a specific offset from the base point is compared, the offset information must be extracted to inform the puzzle. Basically, offset is determined by adding any combination of the three elements: base, displacement, and index. So we get these three elements of tainted operand and then add it. Before the CMP and test compare command is executed, the process of calculating the offset is preceded. There are two types of offset. In register indirect addressing, the offset data is in one of the registers that is specified by the instruction. And in direct addressing mode, the offset data is in immediate value. Offset type is determined at compile time. So how we extract offset? Right branch uses backward taint analysis from tainted branch. From this, it checks which operands are tainted. Because the offset of the comparison value is not important to us, so we have to gather offset of input with the taint information. And next, we analyzing the index addressing modes at the nearby edge blocks, and then extract the offset value of a tainted operand. And byte sequencing. Byte sequencing is necessary when comparing strings byte by byte. In order to insert it to dictionary, we have to join it. First, we identify one byte character in the output file of right branch, and then sort in ascending order of instruction addresses where the extract value existed. And we check offset value to sequentially join the byte strings, and represent a sequence of bytes and save string to dictionary file. At demo time, you can see the result of joining each byte. This is the architecture diagram of our generation-based puzzle. We know the target binary, and then right branch runs the input and creates the dictionary file before pausing, and then pausing with the extracted input. Okay, now we would like to demonstrate and show a demo video. In this demo, I am going to show you our right branch. We have prepared sample programs and the other binaries for demo. So let's see in action. First demo file is a simple C program that has three comparison branches. This is main function. And here is the compare string. Main function has a single comparison branch in for loop, and compare 4 byte strings byte by byte. Second comparison branch is in full function. It compares string with the standard library function. And so the comparison branch is a nested branch like this. All different types of comparison branches in this program. So let's actually start it. To execute the right branch, we need to specify where the sample program is. Then we can execute the right branch with some options. This program takes the string as the input. So we have to insert the input value like this. And this is the output of right branch. You can see that we are automatically creating 3 comparison values. And this number is offset value. Since 2 strings has offset value, we need to join the byte by referencing offset. As a result, 2 strings is joined. and then it created a result file in the same directory. This file format is the dictionary format of American fuzz law. And second sample is the previous one with a pure multiplication. We only modified the offset value in nested branch. Let's take a look again. Unlike the previous result, it prints the HTTP string separated by the offset. And next, we demonstrate two real-world binaries. So the first is object dump, which is command line program. We run knife branch with the object dump binary. And now, let's see saved dictionary file. You can see the command line argument value of object dump. These values are comparison value, which is automatically extracted. Second file is naked FTP, which is an interactive program. I run knife branch again with naked FTP. What we want to do here is firstly we need to insert the input. Let's see the result. There are options used by naked FTP. We can use these dictionaries when purging with AFL. That's very helpful. Okay, this is my end of talk. Thank you for listening. If you have any question, please join Discord server of HITB.